we have, right at the moment, we have two infrastructures listed at Lund University. One is the biomass steam pretreatment, and the other one is an X-ray tomography that is operated mainly by Stephen Hall. I will basically not mention that part of the infrastructure that we have anymore today, more than that we have it. You will have a more detailed description of tomography tomorrow, not from us, but from Luleå, I think it is. Then we also have some infrastructures that has not been listed, but they might be listed if someone shows some interest in that that direction. We had it on our list initially, but it became a quite long list, and I took some examples that we had from that, both regarding material testing and also quite a lot of lignin characterization that we have available, as lignin is one of the research areas that is quite large at Lund University. But I will continue focus on the biomass steam pretreatment, and I thought I put some background into this to begin with. So the biomass steam pretreatment is something that we have been developing for about 35 years or so. And I mean, initially this was done for the ethanol program as a way to either hydrolyze the carbohydrates in wood and other biomasses, or as a way to pre-treat it before enzymatic hydrolysis. But during 35 years, in research, you usually learn to do other stuff than the stuff that you intended from the beginning. So this is not how we use the biomass steam pretreatment today. But we have this long list of different biomasses that we actually have tested. Most of the trees that we have in Sweden has been run through the biomass steam pretreatment at one point or another. Typically, the intention of the steam pretreatment is to hydrolyze the hemicellulose. I mean, it is the easiest part of the biomass, maybe with the exception of the extractives, to remove from the biomass. And the steam pretreatment also opens up the actual structure. Sometimes the steam pretreatment is called steam explosion, and I would say there's still an ongoing debate if the actual explosion makes any contribution to what happens to the material in terms of what we are able to do afterwards with it. But biomass, I mean, it contains 4 different classes of components: extractives, hemicellulose, cellulose, and lignin. And if we want to make something of I mean, these different fractions are quite different from each other. And if we want to put value into the biomass, we need to somehow extract or fractionate the biomass so that we can work with the individual components rather than the entire biomass. Now, different biomasses have different compositions, and since we come from the bioethanol field, we also have agricultural biomasses that we have been tested, and this is just as an example of how the composition will vary depending on material, and this has some impact on what is possible to do with steam pretreatment. And I mean, the main differences, if we then look at trees, for instance, that's between hardwood and softwood, and the composition of the hemicelluloses, also extractives, of course, but where we in the softwoods have typically the main hemicellulose being galactoglucomannan, and in the hardwoods it's mainly a xylem-based hemicellulose, which will influence both what we can do with the extracted hemicellulose and how we operate the steam pretreatment. Then, I mean, ways of fractionating biomass. I mean, this is something that we've been doing in the pulp and paper industry for a long time. I mean, existing products from wood is, I mean, fuel, of course, but also pulp and paper by very many different processes, and also, of course, different kinds of biofuels. And these are to some extent based on fractionation processes. At Lund University, I mean, we have had the ethanol research ongoing for quite a long time, and now there's quite a lot of focus on lignin, of course. Everyone wants to do something with lignin, but also on the sugar platform. And Department of Energy had a couple of years ago these 12 likely new platform chemicals that could make an influence in the future, and all of them are based on glucose. And I only have these as an example. As I mean, we have two paths to making material out of wood, and it's either preserving the structure that we have in some way or form, or fractionating and preserving the structure of the lignin and so on, or it's break it down and build it up again. And this is an example of breaking it down and building it up. But my point here is that the problem is that this picture, that the last picture I showed, is only focusing on one component. And what do we do with the rest? And the point here is that fractionation of the biomass is, to me, the challenge, because the hemicellulose is something that we can extract in either monomeric, oligomeric, or polymeric as a polymeric fraction. The lignin, yeah, well, we don't really know what we can do with the lignin, but I put mono, oligo, and polymeric there as well, with a lot of question marks afterwards. We simply don't know enough about lignin, I would say. The cellulose, well, you can break it down to monomeric sugars, oligomeric sugars, non-cellulose, or fibers, I would say. But to achieve this fractionation, we need one fractionation process for each pure fraction that we want to produce. So one process will never give us 3 or 4 pure fractions. It's a simple principle of separation technology. You need one process for each component that you want to have pure. Now, in this respect, lignin first has been a buzzword for several years. And I, to some extent, disagree with the lignin first concept, as it goes against quite many process design principles. Because if we look at this picture again, which is easiest to remove? Well, it is probably the extractives. And with extractives, you can produce quite some interesting material and chemicals. Then the second most easiest is the hemicellulose, I would say, in my world at least, because it's, well, to some extent already soluble to begin with. And then it's more or less a tie in my world between cellulose and lignin, but because none of them will easily be soluble. Cellulose is quite recalcitrant, and well, you can make lignin react, but you never, well, you know what you end up with, but it's not always the stuff that you actually want. So the take-home message, and before I start talking about what we can actually do with the steam pretreatment, is that one should know your raw material, and that is something that we typically do know fairly well. Always consider using all of it, not just focusing on the glucose as the Department of Energy top 12 candidates. And don't burn the residue just because it's easy. I mean, combustion of residues has been done for a quite long time in the pulping industry to supply the process with energy. That is something that thinking is maybe something that we need to reconsider in the future. And this is a really, really stupid day to say that there are people smarter than me saying that electricity will be for free in the future. But there are people saying that. I saw what the electricity prices was today, and you might disagree with this statement, but still, nature has given us a palette of material to work with, and has already connected it in a kind of smart way. It's just up to us to unlock the potential of the different fractions that we can actually extract. And with that said, think about the entire process early on. Even if lignin, it is easier in many aspects to burn it than to actually produce something from it with what we know today. But hopefully we will figure something out eventually. With that said, going into the steam pretreatment, and the steam pretreatment is only one process. And with the steam pretreatment, we typically focus on the hemicellulose part of the raw material. The process in itself is very straightforward. Put the biomass in a reactor, heat it up to the desired temperature, which is, with the equipment we have, typically between 160 and 230 degrees. We can't go higher in temperature because that's the limit of our steam boiler, but we can go lower. But it's usually no point in in doing this as steam pretreatment when we're doing this at lower temperatures, because we're moving into the pulping operation rather than a fast process. So the benefit of the steam pretreatment is that we have a rapid heating up of the material. We have it at that temperature for a fairly short time. It can be 1 to 30 minutes, and 30 minutes is to us a really long time. Typically we are working in the 5 to 10 minutes span, and then you release the pressure down to atmospheric, and then you have a flashing of the steam that is in the material, and the temperature drops fast, and you're then also basically quenching reactions that is ongoing. And since quite a lot of stuff happens in terms of reaction in the first 5 to 10 minutes, it's important to stop the reactions fast, which is easy to do in this way, but more difficult to do when you want to do it with a heat exchanger, for instance. And I have a couple of pictures of what the material looks like after the steam pretreatment, and you will probably agree with me that sending that material through a heat exchanger is not very smart. What we can do to tweak this process is to, of course, play with the time and temperature profiles during the steam pretreatment, but we can also add catalysts along the, well, we add it from the beginning, but I would say that some catalyst could actually be added during the process as well. Typically, if you want to produce a monomeric sugar solution, you would typically add an acid. Sulfuric acid is always a cheap and simple option, but there are other acids available. Some of them are better or worse in terms of if you want to think about the process and scaling up, but they can probably produce interesting results. You can add alkali, and I mean, in order to keep this process at a neutral conditions, you need to add some alkali, since the acetic acid groups on the hemicellulose that is released during the pretreatment will lower the pH. So you can add alkali to keep the material neutral, and you won't get as much hydrolysis of the hemicellulose. You will get an oligomeric hemicellulose fraction instead. And you can, of course, bump the pH even more and get longer chain hemicelluloses. Depending on how you do this, it will also affect the time and temperature needed for the process, and it will, well, not to some extent, it will affect the yield of the hemicellulose that you can extract. Because when you're doing this as an hydrolysis, you can actually cleave it from bonds to the other components, while if you're just extracting it, if it's covalently bound to something else, it won't extract as well. So this is the schematic of what we're doing in terms of biomass steam pretreatment. And then if we look at what the equipment actually looked like, it is a reactor. And I mean, this looks like a quite large equipment, but the reactor is actually this 10-liter vessel here. I hope that you can see that I'm pointing on my screen now. I don't know if this works. And the rest of the equipment here is basically the flash vessel where we collect the material after the bottom valve here has opened. And the boiler, steam boiler, is located behind it. Now, this is a batch reactor. We have two of these, one 10-liter and one 4.5-liter reactor. The smaller reactor also has the benefit that we can actually use indirect heating. So if we have a very, very wet material, which we typically try to avoid, but if we have a wet material, we could actually supply energy from a jacket rather than pushing in steam to heat the material. Now, batch processes, especially short time batch processes, is with biomass is a problem because the filling time of the reactor will take and emptying will take a long time in relation to the actual reaction time that we have. So it is beneficial to work with continuous processes instead. And at the pilot plant or demo plant that is currently operated by Rice in Åkersvik, they have a continuous steam pretreatment rather than the batch pretreatment that we're working with or has been working with. What we learned from the collaboration with SECAB at that time was that the material has different properties when it's being continuously pretreated, but we were never able to understand why, because the flexibility of the demo plant is it's not as flexible as the batch steam pretreatment. So 5, 6, 7 years ago, we got ourselves a continuous steam pretreatment that we are able to work with. And this looks a little bit like something that Professor Balthasar, those of you that were around in the 80s, has built. It's huffing and puffing, but it produces a steam pretreated material. And we are able to work with basically the same kind of material and same conditions. The maximum temperature is a bit lower with the continuous steam pretreatment, but still. And the scale is larger. So instead of working maybe at 10 kilos a day, we're working with up to 10 kilos an hour, depending on the material. So we can produce more material for more extensive testing. So it's a pilot plant rather than a bench scale plant, even though that it might be difficult to call this, if you look at it, a bench scale, but the continuous plant is actually smaller in footprint. So the pre-treated material afterwards, if we, for instance, take a wood raw material, we mill it down to something that is easy to handle. we can basically work with pulp chips, but the feeding of the wood chips then into the reactor is more tedious, and if we mill it a little bit more and can be able to pour it in. And out comes something that, well, best described as something that looks like shoe polish, or if you're a little bit mean, it looks like cow shit. But what has happened with the material is that we have partly or entirely hydrolyzed the hemicellulose. So if we squeeze the liquid out of that brown stuff, we have a hemicellulose-rich fraction. And we have opened up the structure for further processing. If we then do this with straw instead, the straw hemicellulose is easier to hydrolyze. So we need to go down in temperature, maybe up in time a bit, but definitely less acid added to achieve the fractionation that we want. And when we then have done this steam pretreatment and fractionated out our hemicellulose, we still have the lignin and the cellulose to do something with. And I mean, there are tons of pulping operations available. And I took an example here just because, I mean, this has not to do anything with the infrastructure as such, but it might fuel some ideas. So we started with a hardwood and did two different steam pretreatment conditions, one mild and one more severe, and achieved some fractionation of the material. The severe steam explosion is what we call it in this paper, just because then we could call it STEX, and it made it nice together with the hydrotropic extraction that we call the hex, so STEX and hex. We can see from the middle pie charts that we, with the severe pretreatment, we remove more of the hemicellulose. We don't take all of it. It's very, very difficult to take all of it without destroying the stuff that is left over. And then we've done this hydrotropic extraction to remove lignin from the material. And from the right pie charts, we also see that what we did in the steam explosion or steam pretreatment had a quite dramatic influence on what actually happened in the hydrotropic extraction. So when you're putting together a process, steam pretreatment can be one part of what is needed to achieve a good biomass fractionation. And that is basically my take-home message. To be able to utilize the entire biomass, a process for removing the hemicellulose might be needed. And with this biomass steam pretreatment, we can do that. And at the same time, condition the rest of the material so that it works well in the coming processes.